Hello there, Mr. Sutton here, bringing you the Algebra 2 8-4 lesson on independent and dependent events. In this one, we are going to be determining whether events are independent or dependent, and we're going to be finding probabilities of these two different types of events. We're going to start this one off with a question, little food for thought. Let's say you draw two cards from a standard deck. The first time, you put the card back before drawing again. The second time, though, you just leave the card out. Do you have the same probability of drawing two kings in both of these situations? Why or why not? Alright, so if you pondered this a bit, you probably realize that if you put the card back in, you're kind of starting over. So you have the same probability for drawing each king, whereas if you leave the card out, well, that changes that second probability because now there's fewer cards in general and specifically fewer kings. So these two different situations highlight the difference between what are called independent and dependent events. Independent events do not affect each other's possible outcomes. So these are events that, it doesn't matter what happened in one event, the other event is completely unaffected, and you can kind of treat them as different problems. Kind of like flipping a coin and rolling a die don't affect each other. So in this case, we just have to multiply the individual probabilities to figure out the probability of both of them happening. So if you like a formula, we could say the probability of A and B is going to be the probability of A times the probability of B. So if you can figure out those individual probabilities, you just multiply them and that's all there is to it. So these are fairly straightforward. But now, what happens if your events do affect each other? What if we have dependent events that do affect each other's possible outcomes, like drawing a card and leaving it out and then drawing again from a modified deck? Well, in this case, we can't just multiply by the individual probabilities because this second probability will have changed. So in this situation, we need to multiply by the conditional probability of the second event, given that that first event has already happened. So the formula is similar, but a little bit different. Now we have P of A and B equals, still we have that probability of the first event, but now we need to multiply by P of B given that A has already happened. So this is a little bit of an adjustment we're going to have to make when we find a dependent situation. Since, as you probably noticed, we have two different formulas, one for independent, one for dependent probability, it's kind of important to know which situation you're dealing with when you tackle a problem. So these first two questions here, first two big examples, we're just going to be figuring out whether we have independent or dependent events. And that's it. So take a look at these two situations. In the first one, we have a student taking a quiz, randomly guessing answers to 4 of the true-false questions. We want to know if guessing the correct answer on question 1 and guessing the correct answer to question 2 are independent events. And in the other situation, we have 4 students with 1 boy and 3 girls. Teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. So again, the question is, does one event affect the sample space, the possible choices for the other event? Pause the video and try each of these out. Alright, so for question 1, it doesn't really matter what I answer to question number 1 in the problem here. That's not going to impact my answer on question 2 if I'm just randomly guessing. So since answering one question doesn't change the possible outcomes for the other question, I still have a choice between true and false regardless of what I answer the first time, that would suggest that these are independent events. Now down here, when I pick a girl for the for the speaker and then what are my chances of picking a girl for the second event, the person that I pick for that first event is going to impact my decision space for the next event. If I pick one girl for the speaker, then that's only 2 girls instead of 3 girls that I have to be able to pick for the recorder. So since the speaker choice changes my options for the recorder choice, we would say that these are dependent events. For this next problem, we have a satellite TV provider surveying customers in 3 cities, and the survey asks whether they recommend the provider to their friends. The results as joint relative frequencies are given in this two-way table. Our question is, we want to know if recommending the provider to a friend and living in Long Beach are independent events. I guess another way of asking it is somebody who lives in Long Beach more or less likely than kind of the general population to recommend that provider? So a quick way of figuring out from a table whether things are dependent or independent is to kind of look back at our 2 formulas we had. Those formulas for independent and dependent were exactly the same, except that one formula you were just multiplying by P of B, the other you were multiplying by P given A, or B given A. So if you want to figure out if these are independent events, then you really just need to figure out are P of B and P of B given A roughly equal. If A and B are independent, then these 2 things will be roughly equal. If they are dependent, then you're going to see a decent difference in them. So in this case, the 2 different events they told us here are recommending the provider to a friend and living in Long Beach. So pause the video and see if you can use this type of reasoning to figure out whether these are independent or not. Okay, so our 2 events again, living in Long Beach and recommending a friend. Let's just think of recommending our friend, yes, as kind of our event B in this situation. So what we're going to do is we're going to figure out if the probability of just yes, regardless of location, is roughly the same as the probability of yes given Long Beach as the location. So let's figure out yes first. To get that probability, I just need to add my 3 yeses together here, 0.29, 0.27, and 0.32. Let me get out the calculator. So 0.29, 0.27, 0.32 comes out to about 0.88. All right. Now we want to know if this is roughly the same as yes given Long Beach. So to do the conditional formula there, I have to do the probability of yes and Long Beach, which is 0.32, divided by the probability of just Long Beach, whatever the condition is. So that's going to be 0.32 plus 0.04. And let me go to the calculator for that one. So do a fraction, 0.32 in the numerator, 0.32 plus, let me get a decimal in there, plus 0.04, and this comes out to about 0.889 if I round it off. Now, are these exactly the same? No, but I would say they're close enough. I would say if you match at the 100th or 1000th place, then that is good enough. So I think we can conclude here that these are independent of each other. For the next couple of questions, we're actually going to find some probabilities. So in both cases, your first task is going to be to figure out whether you're dealing with independent or dependent probability, and then use the appropriate formula and see if you can take it the rest of the way. So for this first one here, we have a spinner divided into equal parts. We want to find the probability that we get a 5 on the first spin and a number greater than 3 on the second spin. Pause the video and give it a shot. All right, so for these spins, one spin does not affect the decision space for another spin. It's not like I'm going to take a number off the wheel once I've spun it, right? So since these don't affect each other, these are independent events, and we can just use multiplying probabilities together without finding any conditional probability. So let's label our events. Let's say that, and we're using this formula here, multiplying P of A times P of B. So let's say that A is spinning a 5, and let's say that B is getting a number greater than 3. Let's find our individual probabilities first. So probability of spinning a 5, well, there's 8 of these with equal areas, so that's just going to be 1 out of the 8, 1/8. Probability of spinning a number bigger than 3, we again have 8 total to choose from, and there are 1, 2, 3, 4, 5 of those that are larger than 3, so 5/8. So we just have to multiply these together, 1/8 times 5/8, which is going to come out to 5/64. For this next problem, we got a bag o' money containing 20 $1 bills and 5 $10 bills. You randomly draw a bill from the bag, set it aside, because why would you put the money back, right? And then randomly draw another bill from the bag. We want to find the probability that the first bill is a $10 bill and the second bill is a $10 bill. Pause the video and give it a try. Alright, so because we're not putting that first bill back in there, that's affecting our options for that second draw. So because of that, because our first draw affects the sample space of the second, these are dependent events, and we're going to have to use our dependent formula. P of A and B equals P of A times P of B given A. So let's find A first. So this is the probability at the beginning of that first $10 bill. Now initially there are 5 of those $10 bills in there, so we're going to have 5 over something. 21s plus 5 10s, that's going to be 25 overall. And since we are going to be multiplying these later on, it's probably a good idea to reduce this right away, so 1/5. Now we also have to find our conditional probability of B, so that second bill. So once I've drawn that first $10 bill, there are now only 4 of those $10 bills left. So we're going to have a 4 for the numerator on this one. And we also have 1 fewer bill overall. So instead of 25, now we're down to 24. So we have 4 over 24, which I could reduce if I wanted to 1 over 6. Now that I have these, I can just multiply 1/5 and 1/6 together, and that gives me 1 over 30. Now this is in contrast to if you put the dollar bill back, then you would just have 1/5 times 1/5 again, which would be 1 over 25, slightly higher probability. So it does make a bit of a difference. So that's it for this lesson. I'm going to take the money and run. Till next time, Mr. Sutton signing off.